Have you ever really looked at the pipes all around us? I mean, they're everywhere, in our walls, under our streets, in these huge industrial plants. They seem so simple, right? Just tubes. But they're actually governed by these incredibly powerful, hidden physical laws. So let's peel back the layers and see the invisible engineering that literally makes our modern world flow.
So get this. This was a real-world problem for the Atlantic Sugar Facility up in Alberta. They needed to move tons of sugar beets with water. But think about it. If you go too slow, the beets just sink and clog up the whole system. Go too fast and you basically create beet pulp, damage the product, and you start tearing apart the inside of your pipes. The solution? It's all about a super delicate balancing act.
And it turns out, solving a puzzle like this one, well, it shines a spotlight on the fundamental dilemma that's at the heart of all piping design. It's this constant push and pull between two opposing forces that every single engineer has to wrestle with.
Okay, so you've basically got two main levers you can pull. On one side, you have velocity. You need enough speed, right? That's what keeps solids like those sugar beets suspended in the water. But crank up the velocity too much and your energy bill goes through the roof, you start eroding the pipes, and the whole thing gets incredibly loud. Then, on the other side, you want to keep your pressure drop as low as possible. Now, that's just a fancy term for the energy you lose to friction. A low pressure drop is great for saving energy, but if it gets too low, your velocity drops and, you guessed it, all your solids settle out and you're headed for a massive clog.
So here's the bottom line. It's never about just cranking one thing up to the max. It's always about finding that perfect, most economical, and safest compromise between them. This is the central challenge, and we're going to break down exactly how it's done. To even begin to control velocity and pressure, you have to know the exact dimensions of the field you're playing on. But here's the thing with pipes. What you call it isn't always what you get, not even close. Okay, let's talk about something called nominal pipe size, or NPS. You'd naturally think a 4-inch pipe is, 4 inches wide somewhere, right? Well, for most of the pipe sizes we use every day, that number is just a label. It's a standard name, not an actual physical measurement of its outside diameter. And this is what's so wild. Take a look at this so-called 4-inch pipe. The outer diameter always stays the same at 4.5 inches. But as you make the walls thicker, that's what schedule means, the inner diameter, which is the actual path the water flows through, it shrinks a lot. You go from a Schedule 40 to a Schedule 160, and you've lost almost a full inch of flow area. And this right here, this is the first hidden law. The inner diameter is the only dimension that actually matters for flow calculations. So an engineer has to completely ignore the label and find the true physical area where that fluid is going to travel.
So, once we know the real size of our pipe, there's another key factor we have to figure out. We need to understand the behavior, you could even call it the personality, of the fluid that's inside it. Because it turns out, not all flow is created equal.
This is the next fundamental question an engineer has to answer. Is the fluid moving in these nice, neat, orderly layers, or is it a swirling, chaotic, tumbling mess? The answer to that question has a massive impact on our old friend, pressure drop. And the tool they use to figure this out is called the Reynolds number. Now, don't worry about memorizing any formulas. Just think of it as a single number that basically describes the fluid's personality. It's kind of the difference between, say, slowly pouring honey versus turning on a fire hose. One is very orderly and predictable, the other is total chaos. The Reynolds number tells you which one you're dealing with. So if you have a low Reynolds number, you get this beautiful, smooth, predictable flow called laminar flow. But as you speed things up, you hit a tipping point where the flow just breaks apart and becomes turbulent, full of these chaotic, swirling eddies. Now that turbulence is actually great for keeping sugar beets suspended, but it comes at a cost. It creates way more friction and energy loss. Okay, so we've got the pipe's true size, and we know the fluid's personality. Now we need the master key, the one single equation that can combine all of these factors and predict the final, absolutely critical number, the pressure drop.
And that equation is called the Darcy-Weisbach equation. We're not going to get into the nitty-gritty math, but just think of it as the universal law of the land for calculating friction loss in a pipe. It's just so powerful because it takes everything into account. The pipe's real inner diameter, the fluid's speed, its viscosity, even how rough the inside surface of the pipe is.
And that's its superpower. See, there are simpler formulas out there like Hayes and Williams, but they're really only accurate for plain old water. Darcy-Weisbach is the gold standard because it works for pretty much anything you can shove through a pipe. Natural gas, chemical slurries, you name it. That makes it absolutely essential for process engineers. Now, so far, we've only been talking about nice, straight pipes. But let's be real. Real-world systems are more like an obstacle course full of twists, turns, and valves. And every single one of those obstacles adds a massive amount of friction.
Just look at the insane, chaotic path the fluid is forced to take inside this one valve. It's incredibly turbulent. A single elbow or valve can create as much pressure drop, as much friction, as dozens of feet of straight pipe. You absolutely cannot afford to ignore them in your calculations.
So, how in the world do engineers account for all this chaos? Well, they use something called a K-factor. The best way to think about it is like a handicap in golf. A straight piece of pipe that has a handicap of 0. But a sharp 90-degree elbow might have a handicap of, say, 30. A really complex valve could have a handicap of 100 or more. Engineers look up these numbers in legendary handbooks, add them all up, and that gives them the total friction for the whole shebang. All right, let's bring this all the way back to our sugar beets. Now that we have all the tools, the true pipe size, the Reynolds number, Darcy-Weisbach, and K-factors, we can finally see how an engineer solves the puzzle by applying these hidden laws. So here's how it goes down. First, they pick a trial pipe size, and they use that real inner diameter to try and hit their target velocity. Step 2, they calculate the Reynolds number to make sure the flow is turbulent enough to keep everything suspended. Then, step 3, they use the Darcy-Weisbach equation and add up the K-factors for every single valve and fitting to predict the total pressure drop for the whole system. And finally, step 4, they check. Is that pressure drop acceptable? Can the pump handle it without costing a fortune? If the answer's no, well, they pick a new pipe size and run all the numbers again. And that's the solution. It's this meticulous process, a perfect compromise. A successful design isn't about being the fastest or having the lowest friction in one area. It's about finding that sweet spot, that optimal balance between every single one of these competing forces. And look, this isn't just some niche problem for a sugar beet factory. These exact same principles, balancing velocity against pressure drop, understanding the true pipe geometry, figuring out the fluid's behavior, they govern pretty much every fluid system that makes our world work. From massive natural gas pipelines to the equipment making life-saving drugs, even the plumbing in your own home. So the next time you turn on the tap or you drive by a sprawling refinery, remember the hidden laws of the pipe. Think about those invisible balancing acts, the constant engineering trade-offs between cost, safety, and performance that have been perfectly solved just to make it all work so seamlessly that you never even have to think about it. What other hidden trade-offs are out there, shaping the world around you?